Hello everyone, my name is Ajay Mittal. There are today's video is going to be about move semantics. It's part of the modern C++, and it's a topic, and I'll be talking about other modern C++ topics in other videos. The material for this video is at this link mentioned over here. It's only accessible within US, and the source code that we'll discuss in today's video is available on GitHub at this link. So let's get started. Um, Move semantics let us use temporary objects, and we need a way to associate or distinguish between temporary objects and normal objects. And in order to understand move semantics, we need to understand what are RValues and LValues. So roughly, RValue is something that is on the right-hand side of an expression or a statement, and LValue is something on the left-hand side. If it has a name, and if we can take the address of something, then it is a LValue. Otherwise, it's a RValue. Now, usually LValues are the things on the left-hand side, but this is not always the case. And we can have things on the right-hand side that are also not RValues. So let's look at this program, values1.cpp. I'm going to open it up in TextPad. Here, I have a function that is returning a constant. Here I have a global variable defined outside any function. And this is a function that is returning a reference, and it's a reference to this variable global. Now let's look at the simple expression int x1 is equal to 100. X1 is LValue. It's on the left-hand side. It's got a name, and we can take its address. 100 is a RValue. We can't take its address, and it doesn't have a permanent address in memory. It may be stored in a register and cleared after the statement is over. Obviously, we can't do 100 is equal to x1 because it's not a name, doesn't have an address. And if we look at the error, we get an error saying LValue required as left operand. Need something we can take an address of, and that has a permanent place in memory. We also cannot do this function is equal to 100. It's returning a temporary object. We can do this because this function is returning an address, a reference to a global variable which exists and has an address in memory. In this expression, x2 is of course a LValue, but this is also a LValue on the right-hand side. And here what we are doing is we are taking the value of x1 and assigning to x2. Here we have a reference x3. It's a LValue because it has a name, and we can take the address of this. The right-hand side is also a LValue. Here we have str1, an object of type string, str2, an object of type string. And this expression passes the compiler. Compiler doesn't complain, but what's on the left-hand side is not a LValue. We cannot take the address of this. So there's an example where we have something on the left-hand side that is not necessarily a LValue. Let's compile this. So we don't have anything output in the program. It compiles and runs fine. Okay. Now we come to something called RValue reference. This is a new concept introduced with C++11. We had references prior to C++11, of course, and we refer to those as LValue references. A RValue reference is initialized with the R value, and a LValue reference is initialized with a L value. And every type can have a L value and a R value, even a R value reference. Now, if we take a simple example, such as int x is equal to 1, the type is int, and it's got a L value, which is x1. It's also got a R value, which is 10. And we shall see how a R value reference can have both L value and a R value. Okay. So let's take a look at this program ref1.cpp. Here I've got a template function isValue, and we'll come to the syntax a little bit later on, but it's calling another system function called is LValue reference, and this basically returns true or false depending on if T is a L value or R value reference. Here I have a function. The function takes a single parameter, which is a L reference, and this is a R value reference. And what this means is when I call this function, I should pass a L value in it. And what this is saying is when I call this function, what I'm passing in the argument should be a R value. I'm just checking over here, is A1 a L value, and printing something out here. Now notice since A1 is a name, this is going to be true every time, because even though it's a R value reference, it has a name, so it's a L value. But when I call this function, what I pass into it is a R value. Here I've got two variables, x1 is equal to 10, y1 is equal to 30. This is just a manipulator which is stating print true or false. Here I have a R reference, R value reference, and I have to initialize it with the R value, so I initialize it with the constant 20. This is another R value reference initialized with 30. Here I have a L value reference. I cannot initialize it with a constant. I have to initialize it with the L value, and I choose the variable x1 to initialize it with. Right? So remember, L value is just another name. L value reference is just another name for x1. Right? And here x1r is being given some place in memory because it's a name, but it has to be initialized with a R value. If I same rules that I apply for L value as far as syntax goes apply to R value. I cannot just write a R value reference like this. I need to initialize it with something at the point of declaration. I cannot initialize it with the L value. It needs a R value. What am I doing here? I have a R value reference. It has already been initialized. Now x2r is another R value reference. I'm taking the value of this and assigning it to x1r. I'm not changing what x1r is pointing to, right? Or where changing the memory address location. I'm just changing the value of this x1r, and I'm treating x2r and obtaining the value from this. I can initialize a LValue reference with a RValue reference because x1r is a name. If it is a name and I can take the address of it, it's a LValue, and so this works. I cannot do this because a LValue reference needs a LValue to initialize it with. However, if I make the LValue reference a constant, I can do this. I can also not do this because x4r is a RValue reference, and I'm trying to initialize it with a L value. It has to be initialized with a R value. This is okay. I'm passing x1 to it. Remember, x1 is just our variable, and I'm calling function 1 L value reference. So this reference is going to point to essentially x1 when it gets assigned, a1 gets assigned by x1 when I call this function. When I call this function, I have to pass a R value. Why? Because this parameter is expecting a R value to be initialized with. I have a R value reference. I'm changing its value by taking the value of x1 and assigning it. I can also assign a constant value to it if I want. It's not really looking at what the variable types are on the right hand side. It's just taking the value and updating the value of x1r. Same rule applies to a L value reference. When I say is equal to y1, x1l is not now pointing to y1. Whatever it was pointing to was decided at the point of declaration and definition. Now I'm just updating the value of x1l with y1. Same thing over here, except I have the R value reference variable, and I'm taking the value and reassigning and assigning its value to x1. x1 had a value before, but now I'm updating that value with the value of x1r. I cannot do this because x1 is not a R value. This function expects R value. However, I can do this. What the move function does is, this is a part of the move semantics function. It's actually not moving anything, it's changing the type. So it's making the object, whatever you pass it, into a R value, right? X1 was a L value because it was a variable with a name. This makes it into a R value, and now I can pass it to function 2R value reference. If we look at function 2R value reference, it is expecting a R value. x1r is a name. I can pass it to function 1 L value reference. As long as it's a name, it's a L value. Even though it is a R value reference, at this stage, it's a L value. So remember, going back to our example, if we think of for L value reference, if we think of something like this is a L value because it's got a name, it's got an address and location, and this is a R value. Even though the type is a RValue reference, I also have LValues and RValues associated with it. Function R to RValue reference, I can pass it a constant. I cannot pass it a variable name, even though this is RValue reference, because it's actually a L value. If I have something like x2 is equal to 5, this will print 5. The move changes the type to a R value, but the internal value is still 5. It doesn't change the internal value of x2. Let's compile this. So we've got a bunch of things printed out, but at the end we can see 5, 5. Is A1 a L value true? Let's see where that is coming from. This is coming from here. So we are passing R value to it, which is a constant 21. By the time we come over here, we get is A1 a L value, and this prints true that it is a L value. And in fact, at this stage, as we discussed, it will always print true because A1 is a L value at this point. It's got a name, and because it has a name, it has an address. So we've discussed RValue references, but how do we use them? We really haven't seen a use case for this. And this is what we are going to discuss next. Let's look at this file, usage1.cpp. I've got a class here called holder. This is a normal constructor. The holder, by the way, has two data fields. One is a pointer and the other is a size. So I pass the size and allocate that much memory for this pointer to hold. The constructor takes a size value, and we have argument constructor being printed out on the screen. Also print the address of where this object is allocated in memory. Then I create that much memory as specified by size, assign it to data, and update the size variable with size. Here I have a copy constructor, and basically I'm allocating memory and copying the other's data pointer values to my current object's data pointer. And I'm also copying the size. Here I have a R value copy constructor or a move copy constructor. And conceptually, what I'm stating in this function is the other is going to go out of scope soon. I'm really not going to use the other object. Why don't I steal its resources by copying the pointer and the size, and then I set the pointer to null. And I make sure in my destructor for holder, I check if something is null or not. I have an assignment operator. I'm copying the other objects, allocating memory, copying the values. And here I have the move assignment operator, which is taking a R value object, and I'm essentially again stealing its resources. In the destructor, I'm printing out the size that this object had allocated. I'm checking if the M data pointer is not null, and if it is not null, then I'm freeing up the memory for it. Here I have a function create holder, which is returning an object. and it's a temporary object. Here also it's returning an object, but I explicitly state that this is a R value with the move function applied on it. I call create holder. Create holder, it will come to this function, return this function returns a temporary object. That temporary object gets copied over as a copy constructor to H1, right? But what's going to happen is optimization is going to kick in. And the compiler is going to, well, before we do that, let's go through rest of the code. Create holder one, same thing, but comes over here. This returns a R value object that gets at the point of declaration. So copy constructed to H2. And then I call create holder. And I'm not doing a copy construction here. I'm just assigning it to H1. And that's the end of main. Okay. So let's run this and then we'll come back to what the code in the main function is doing. In order to prevent optimization, we can use this minus fno minus allied option for the G++ compiler. All right, so if we look at the beginning code, this argument constructor 1000, this is coming from when it goes inside this function and this temporary object is getting created. It's getting created with our normal constructor, which is here, the argument constructor. This is where this argument constructor gets printed from. When I'm printing the address of this object, the address is this 7 something CC00. All right, so now I've got my temporary object getting created. It returns, and then I should get the copy constructor called for H1, but I don't get any copy constructor. The code doesn't call any copy constructor. That's because even though I told it not to do optimization, it still did it anyway. And what it did is the temporary object that it got created here, it used the same space and basically has H1 pointed to that, right? And I can confirm that by printing the address of H1 over at this line 92, and I see that it's got the same address as temporary object that was created over here. In order to tell the compiler, hey, don't do the optimization, let's try to use one of the move functions, I call create holder one. Create holder one will come over here, and this is converting this to a R value. And now we expect H2's move copy constructor getting called. And that is what is happening at this stage. Once the move copy constructor gets called, and before we come to 99, it's done with the temporary object. So it calls a destructor on that and cleans that up. Now we go to the move assignment. This is creating, I'm getting a temporary object from it and assigning it to H1. And again, that ends up calling the move assignment operator. When I print the address of this H1, I can see it's different from the address that was created for the temporary object. And also the destructor for this temporary object got called. Right? So temporary objects, when I don't need them, I can use their resources. Okay? And so there is a little bit of efficiency, programs become efficient, right? Let's look at usage2.cpp. Here I've got a h1 object getting created. I've got my curly braces here, and h2 gets created over here. And now I say h1 is equal to, I do a move on h2. Remember what move does? It converts L value to a R value. So now h2 is a R value, and we will have the move assignment operator kick in, and that's a function that will be called with this statement at line 89. Okay? So let's run usage2.cpp. We see the move assignment operator getting called over here. Let's discuss default functions. These apply to certain functions such as a constructor, destructor, assignment operator, copy constructor, right? If we don't define them in the class, then the system defines those functions for us, right? As an example, an assignment operator on a class, what it will do is it will do bitwise copy of the object on the right hand side and assign it to the data members of the object on the left hand side. With C++11, we have a keyword default that will explicitly state that the system provide the default implementation. Usually system will create the default implementation for us, even if we don't specify the function, but in certain cases it won't, and we need to use the default keyword. Right, let's take a look at this default 1.cpp. I've got a class A over here, has two data members x1 and x2. It's got a constructor over here. Then I've got a class B, and B has an move assignment operator, right? That's all it has. And then I've got a class C, which is containing a B object. And it's got a default move assignment operator. Now, this part of the code up from line 54 to 59 is just to show a bitwise copy of the default assignment operator. The A object 1 has two data member variables initialized to 10 and 20. The A object 2 is equal to A object 1. What this means is the data members of A object 1, x1 and x2, will be bitwise copied into A objects 2, x1 and x2, so that when I print these values, they should also be 10 and 20. We have C object 1, C object 2. Move, I'm turned this into a R value. C object 1 is going to be assigned to C object 2. Now what's going to happen is, it is not going to do bitwise copy of the data member variable B object 1. It's going to do a move on the right hand side, C object 1, convert this B object 1 to a R value, and then look for an assignment operator of an R value on C, which is this one. So the default move assignment operator gets called. This in turn will do a move on B object 1, and B has a move assignment operator. So it's going to end up calling the B's move assignment operator to assign C objects 1, B object 1 to C objects to B object 1. So let's clarify this with just a simple text thing. We have C object 2, we have C object 1. This has, the C object has a data member called B object 1, and C object 1 also has B object 1, right? It will not be a bitwise copy. The C object 1 has been converted by move to be a R value. It is going to call the default implementation of the move assignment operator. What that in turn will do is, it will call move on B object 1. That becomes a R value, and it will assign that to the B object 1 of C objects 2. So this one has a move assignment operator defined. So this statement should print out on the console. So this is the default implementation is going to do move on the data members of the C object. And if there is a move assignment operator that has been defined for those, it is going to call that. Now we explicitly wrote the code over here so we can see it coming over here. If we didn't have this code, then hopefully it would have called the default move assignment operator for B. Let's run this. So this is default 1.cpp. And we see that the move assignment operator got called. Let's see what this program is going to do. Default 2.cpp. We've got class A, we've got an empty constructor, and we've got a move constructor over here. So let's compile this. Typo there. We get a compiler error. What G++ compiler is saying is, you defined a move constructor, but I noticed that you are trying to use a R value in an assignment, trying to call the move assignment operator. So even though you defined the move constructor, I want you to address the move assignment operator function, right? And we could either define explicitly one ourselves, but it didn't create the default one because we did this. If we didn't have this, then it would have created both the move constructor and the move assignment operator function, right? But we defined one of them, won't let us define the other one, but we can get the default one. We can tell it to use the default implementation by doing something like this, using explicit default keyword. And what it is saying is, I didn't forget about the move assignment operator, just use the default implementation. And this works fine. It compiles fine and runs and does what we expect it to do. So that works. Then we have the concept of perfect forwarding. It applies in certain scenarios. In this scenario, let's say we have a function that takes different arguments. So I've got a class called object, and I've got three overloaded versions of use object. One is taking a LValue reference, one is taking a constant LValue reference, and one is taking a RValue reference. And now I intend to call this function from another function which is a little bit more generic, uses a template parameter. So let's look at our first attempt. We've got the three use object variations, overloaded functions. We've got three versions of the not forward to use object function. This one is taking a LValue reference. This is taking a constant LValue reference and then calling use object. This is taking a RValue reference and calling use object. This is just a sanity check to make sure our use object functions, the corresponding use object is getting called. And here I do the same thing. Let's run this and see what happens. So this was our sanity check. We are calling the right function, the corresponding function. Here, this one, it did what we expected it to do. The use object that called was a LValue reference. This one also did. Let's look at this function. Came over here, called use object X on the constant LValue reference that ended up calling the constant LValue reference over here. Works well. This not forward to use object over here is working with the RValue reference. Came over here. This line should have gotten executed and it did. This is this line. However, when we did use object on X, it did not call the RValue version of the use object, but ended up calling this one, the LValue reference. And we know why it did that, right? That should not be a surprise, because at this point, X is a name. And we know that if something is a name, it's a LValue. So it's not going to call a RValue reference, it's going to call a LValue reference. So let's correct this. What we've done here is we've defined another version of use object called use object 1 that is taking a RValue reference. And over here, instead of calling use object, I'm calling use object 1. This is the same as before, it's RValue. And I know that it's going to call use object 1 at this point, right? Because use object 1 doesn't have a LValue reference option, only has a RValue reference option, which I'm calling with this move x1. Compare it with the other one, which was simply this. All right, fine, that did the trick. We ended up calling the RValue reference use object 1, but we've introduced more functions in our use object. Not only that, the not forward to use object also has three variations, right? Let's see how perfect forwarding helps us overcome these issues. We have the three functions use object as before, but now we have a single function perfect forward to use object, it's taking this T and it's taking T and X. And what this syntax means is X is now a universal reference. It can take both L values, and it can take R values. So when we come here, X has, if we call this function with a L value, it will enter this function. If we call it with a R value, it will enter this function. And then the L value or R value will be preserved by this forward. So when I say use object, forward is stating use whatever X's type was when we came inside the function. If it was L value, we are calling this with L value. If it is R value, we are calling it with R value. And if it was a constant L value reference, then now it's a constant L value reference. The constants, the constantness, the volatile type, L value reference, R value reference, that's being preserved by forward. Because if I didn't have this forward, X is a name, it has an address, it's a L value. So when I call the use object on this, and the other one forward to the right use object will get called. This forward to use object also does the same thing, but as a static cast instead of the forward. This is a little bit easier to read and work with. Okay, we get the right use object, that the function right use object function got called corresponding to whether it was an object, a constant object, or a R value object. So that's the concept behind perfect forwarding. Again, the links to the material are at this website, and the source code is at this website. Thanks, everyone.